In this lesson, I plan to go through the different operations involving radicals. And what I mean by that is I want to show you how to add, subtract, multiply, and divide radicals. Now keep in mind that as the video is being played on your end, you can pause it. So once you kind of think you've got the hang of some of the material, pause, do some of the practice examples that I have posted, and then watch my solutions to see if you've done things properly. And hopefully I don't make any mistakes as I'm doing these. If I do, you can point them out in the comments on our team page. All right, so the first thing is adding and subtracting radicals. And I believe about 3 weeks ago when we were sent home, we had at least decided that we were able to collect together what were called like radicals. And like radicals, let's see here, the term like radicals are radicals that have the exact same radicand. Now the radicand is the number or expression that's underneath the square root sign. So in this one, 8, 12, 318 would be the radicands. So at its face value, we'd say, well, there is no like radicals. There, that will then make us say, okay, well, can I simplify the radicals? Are they in simplest form? So that's going to be our first step in any of these questions, is we're going to simplify the radicals first. So if I look here, I see square root 8, square root 12, square root of 300, and square root of 18. Now we had talked about how we'd like to get to the point where we kind of start to do that in our head, which I'm going to do a lot of these just to refresh your memory. Let's suppose I'll just do this one as an example. If I had the square root of 18, you'll remember we try and find the biggest perfect square that will divide evenly into 18. So the square root of 18 is 9 times 2. So in our head, we can say, well, that's the same thing as the square root of 9 times 2. 9 being a perfect square, so we say, well, that's the same thing as the square root of 9 multiplied by the square root of 2. 9 multiplied by the square root of 2, and the square root of 9 is 3. So 3 radical 2 is a simplified version of radical 18. So when I'm doing that with these numerical ones, I'll just kind of talk about it and do it in our head. So the first one, we've got our 5. I'll just leave that for now. Square root of 8. 8 is 4 times 2, and the square root of 4 is 2, so that simplifies to be the radical 2 radical 2 minus 4. The square root of 12. 12 is 4 times 3. The square root of 4 is 2. Radical 3. 300 is 100 times 3. The square root of 100 is 10. So that comes out here. Radical 3. And we just did this one over here. It's 3 root radical 2. So I'm going to multiply any of these coefficients together. So this one will be 10 square root 2. This one will be 8 square root 3. Subtract 10 square root 3 plus 3 square root 2. So you'll notice we had no like radicals. Well, now we do have some like radicals. I have 10 radical 2 and 3 radical 2. They're both radical 2s. And I have 8 radical 3, or I guess negative 8 radical 3, and negative 10 radical 3. So they're like radicals. So I'm going to group the radical 3's together first. I've got negative 18 radical 3. So I just collect these like I would regular integers. Negative 8, take away 10, negative 18. Now I collect the radical 2. So I get 10 radical 2's plus 3 more radical 2's. So that would give me 13 radical 2's. Now the radicals are different. So I can't go any further. I can't collect those together. I'd be in simplified form, and that would be our solution to that first one. Now, if they involve variables, we looked at that as well. And in order to take the square root of an exponent, you need to be able to take half of it. So x to the fifth would not be a perfect square. So the biggest possible power of x that is a perfect square, that goes evenly into x to the fifth, would be x to the fourth. So when we get into these ones with variables, 2. So this one I am going to show my work, at least for the first couple. So 50 would be 25 times 2. There's your 50. And then x to the fifth, I'm going to make it x to the fourth multiplied by x to the 1. 4 plus 1, there's your x to the fifth. Minus 6x squared. Now the square root of 98x. Well, 98 would be 49 2. Now x to the first, there's nothing I can do with that. So I'm just going to leave it as x to the first. And this one here, 48, 5 here, 48 would be 16 times 3. 16 times 3. And again, the x is already in simplest form. There's nothing that I can do with that one. Okay, so now if you look at this one, I'm just going to switch colors here. 25 is a perfect square, and x to the fourth is a perfect square. So when I take the square root of 25, I get 5. I multiply it by the 2 that's already out there. I'm going to get 10. The square root of x to the fourth is x squared. Radical. 2 and the x would be still left underneath here. Minus square root of 49 is 7. None of these other ones are perfect squares, so all I'm going to do is bring this one out here. So it's going to be minus, I'm going to multiply it by this, so that'll become minus 42 x squared, radical 2x. 16 is a perfect square. None of these other ones are perfect squares, so it's going to give me, square root of 16 is 4, multiply it by the 5 that's already out there, 20, square root, what's left underneath here, 3x. Now when I look at the radicals, this one is a radical 2x, and this one is a radical 2x. And in front of them, they're both algebraic terms that have a variable part of x squared. So I am going to be able to group these two here together. Now this one's not the same radicand, so we can't get grouped with these two. But these two we are going to be able to collect together and say, well, I got 10x squared, radical 2x, subtract 42x squared, radical 2x. So if I group those two together, I have negative 32 x squared, that's these two collected, and then the radicand never changes, it just stays radical 2x. And then this one, there's no other radical 3x's, so it'll just stay by itself. And that would be your final answer. I have another one here down below. So this one's got variables in it again. Now this time the index is 3, so we're doing cube roots. So I'd be looking for perfect cubes that divide into these numbers, not perfect squares. So it's going to be 7 plus 2. Now your perfect cube, so the first perfect cube is 8, and 8 goes into this one. So I would write it as 8 times 2, and w to the 9th. In order to be able to take the cube root of an exponent, you need to be able to divide it by 3 this time. Now, last time it was 2 because it was square root, but this time it's cube root, so you need to be able to take a third of your exponent, which I already can. So that one's just going to stay the way it is, minus 5w squared cube root 54. So I need a perfect square that goes into 54. And ideally, we'll always want the biggest perfect square. So the biggest perfect square here would be 27 times 2. This is divisible by 3, so that will just stay as it is. All right, so let's keep going here. We'll clean this mess up a little bit. Need some more room. All right, so now I still have my 7 plus. Oh, this is cube root, not square root. So the cube root of 8 is 2, multiplied by the 2 that's already out there. I'm going to get a 4. And then the cube root of w to the 9th, so I take a third of the exponent, is going to be w to the 3rd. Cube root, there'll be a 2 left underneath there. Minus. The cube root of 27 is 3, multiplied by that 5 is going to give me a 15 out front. I have w squared. The cube root of w to the 3rd, so I take a third of the exponent. That will give me a w, which I have to multiply by the w squared that's already out there. So that will give me w to the 3rd, leaving me with cube root, and just the 2 will be left underneath here. Well, as you can see, I got a cube root 2 and another cube root 2, and we're going to collect those together then because they're like radicals. The index is the same, the radicand is the same. So when I collect that stuff all together, I've got my 7, that just stays there. 4w cubed minus 15w cubed, they're both cube root 2's. So that's going to give us, actually, we're going to put it as a, so rather than a plus, I'm just going to make that, and that because it's negative 11 when you group those, so it's negative 11 w to the third cube root of 2. And now remember, this is all one term. So sometimes students are tempted to say, oh, can I do anything here with the 7 and the minus 11? No, you cannot, because this is all connected together. The only thing you could do is collect it with other cube root 2's like you did up above. So this 7 just keeps hanging around out front, and that would be part of our final answer. Okay, so at this point, I would suggest you have a look at this checkup question. Perhaps pause the video and try it on your own. Write the question down, try it on your own first, and then turn the video back on to see my solution. So I'm going to go through the solution to it here now. Now this would be a challenging one that, yes, I'd expect you to be able to do, but you need to know your stuff if you're going to get this question correct. Okay, so you'll notice first of all we've got 2 square roots and 2 cube roots. So make sure you always pay attention to the index, because that will dictate whether you're going to use perfect squares or perfect cubes when you're trying to reduce your radicals. I'll start with this one. The square root of 20 is divisible by 4. So 4 times 5. The square root of 4 is 2. Multiply that 2 by that 3. So this is going to reduce to 6 square root 5 minus cube root now. So this one, I think because it has the variables in it, I think I'll write it out. So cube root 40. So the biggest perfect cube that divides evenly into 40 is 8 times 5. A to the 7th. Now that 7 will not divide by 3. So we are going to rewrite a to the 7th as the biggest perfect cube root, which would be a to the 6th, multiplied by a to the 1st. And then 125 is divisible by 25. So this would be 25 times 5. The square root of 25 is 5. Square root of 5. This one here I'll write out again just because of the variables. I find it easier if we can see what we're doing. Cube root of 320. So I need to find the biggest perfect cube that goes into 320. So it definitely goes by 8. 320. Grab my calculator here for a second. 320, if I divide it by 8, goes 40 times. But 40 is also still divisible by 8. So there must be a bigger perfect cube I could use. So 4 to the power of 3 is 64. So I think 320 will divide evenly by 64 if we go 5 times. So this is the same thing as 64 times 5. Now a to the 1st, I can't reduce that any further, so it's just going to stay as a. Now underneath here, that's a perfect cube. In this one, 8 and a to the 6th are perfect cubes. So we are going to do these two perfect cubes are going to reduce those a bit further. So 6 radical 5 doesn't reduce any further. All right, so the cube root of 8 is 2 multiplied by the 5 that's out there already is going to make that a 10. The cube root of 8 is the 6. So now remember, you need to take a third of the exponent. So 6 divided by 3 would be 2. So that's a squared multiplied by the a will give me a to the third. And then that will leave us with 5a underneath the cube root symbol. Minus 5 radical 5 plus. So we got to do some more reducing here. So the cube root of 64 is 4, because 4 times 4 times 4 gives me 64. Multiplied by the a to the third that's out front, I'll get 4a to the third cube root, and the 5a will be left underneath. Well, I now have this square root and this square root have the same radicand, so I can group those two together. 6 square root 5, take away 5 square root 5 is just 1 square root 5. And now I've got 2 cube roots that are the same index and the same variable parts out front, so I'm going to be able to group those together as well. Negative 10a cubed, cube root 5a, and a positive 4a cubed, cube root 5a would group together to give me negative 6a cubed. Just collect the like terms like you normally do with algebra. Cube root 5a. And that would be our final answer. So if you're looking for practice in your textbook, and you may say, oh, I don't have my textbook at home. That's fine, because on our Teams page, the PDF version of the textbook is there. So these are just a series of questions on addition and subtraction. Now, again, I'm not saying you do all of those. Pick and choose a few here and there. Answers are in the back. So it's a really good way to just kind of give yourself a sense of some mastery of the concept. All right, so we're going to now move into multiplying and dividing radicals. So in normal conditions, I'd probably hand out this sheet and get students to just practice. It's all kind of the prerequisite skills you would need and should have accumulated to be able to do multiplying and dividing radicals. So I've just picked out 4 examples from these. I have them here in the next slide. And again, you could stop your computer or your video and try these 4 on your own. I'm going to now go through the solutions to them. Okay, so the first one is just basic algebra. And it's a binomial multiplied. There's nothing in between here, so they're multiplied together. So we have to multiply everything in this bracket by everything in this bracket. So basically it's going to be 3x times x, 3x squared, 3x times negative 2y will be negative 6xy. Negative 4y times x is negative 4. Now the order you put these letters in doesn't matter, so I'm just going to put it as xy to keep it the same as that one. Multiply these 2 together, you're going to get a positive 8. Multiply the y's together, and you'll get y squared. Generating 2 like terms in the middle, so we'll gather those together. 3x squared, subtract 10xy, plus 8y squared. That'd be it. Nothing else collects together. You would be finished. So that's multiplying 2 binomials, which is a skill we're going to need to use, obviously, in the context of radicals, though. All right, I go over this one. So this one's a monomial divided by a monomial. Well, in that situation, what we do is the numbers in front, we divide as normal, or if they don't divide evenly, at the very least, you would reduce them. Now, these ones are going to divide evenly, so negative 6 over 3 is going to give me negative 2. When you divide variables that are the same, you subtract the exponents. So x squared, this is x to the 1, so I'd subtract those, and I would just get an x. Now this y, there's no y to divide it by down here, so that would just stay as a y. And that's it. So that's dividing a monomial by a monomial. Now down here, the first one we've got is a monomial divided by a binomial divided by a monomial. And we'll go through how we do that. So this one, when you have multiple terms, and you say, what do you mean by terms? Well, terms are subtracted by a subtraction or addition sign. So this would be 2 terms. 4t squared would be a term, and then 12t would be a term. So technically, each of these terms are divided by the number on the, or the expression on the bottom. So you can't just divide it into this one and then it all of a sudden disappears. So technically, it means this. 4t squared is going to be divided by negative 2t, and then minus 12t, which is also needs to be divided by minus 2t. So when you do this division, 4 divided by negative 2 is negative 2. T squared divided by t, subtract the exponents, you get t. Now negative divided by a negative, that's going to be a plus. 12 divided by 2 is 6. T divided by t, if you subtract exponents, it's 1 minus 1, which is 0. So t to the exponent 0, anything to the exponent 0 is 1. So essentially those have divided each other out, and you're just left with negative 2t, subtract 6. And over here we have some addition, subtraction of some radicals, but we also got to know, well, how do I manage these signs out in front? Now, a common mistake students make here is they say, oh yeah, okay, I got to multiply this by others. No, it's not multiplying, that's addition. So this addition needs to go through here, and this subtraction needs to go through all of these. The plus signs, students usually don't have too much trouble with. What happens here is that this negative, students will often fail to realize it needs to distribute to both of these. So this first one, not much I can do with the 8, I'll just rewrite it as 8. So I'm just going to kind of I'm going to get rid of the bracket. So it's 8 plus the square root of 18. So 18 is 9. I'm going to reduce the radicals as we're going here. 18 is 9 times 2. The square root of 9 is 3. X squared is also a perfect square, so the square root of that is x. It would come out front. I'd be left with a 2 underneath there. Plus 2, plus 2. This plus goes to here, so that's not going to do anything. 8 reduces, so it's 4 times 2. The square root of 4 is 2. The square root of x squared is x. And remember, we said this was 4 times 2, so there's still going to be a 2 left underneath here. Now, this is where you got to watch the negative. So this negative goes into here, which most will get that sign right, but it's this one that students will mess up. This negative needs to distribute into here, which is going to make that a plus. And now we're going to reduce this. So 50 is 25 times 2, so that would be 5. The square root of x squared is x. Remember, we said it's 25 times 2, so there's still a 2 left here. Well, now you've got some like radicals. This one, and this one are all radical 2. So let's collect those together. And it doesn't matter whether you put the number first, the radicals first. It's really kind of your preference. I'll do the radicals right now. Let's collect those. 3x radical 2 minus 2x radical 2, that would just be x radical 2, plus 5x radical 2 will give me 6x radical 2. And then I've got an 8 plus 2 and a minus 5. So I'm going to group those three together. So 8 and 2 is 10. Take away 5 is minus 5. All right, so that's just some of the kind of prerequisite skills we hope you'd have as we lead into and start looking at multiplying radicals. So there's basically a property that says if you multiply any two radicals together, if now the indices, the index here and the index here, they have to be the same. So that's basically saying you can't multiply a square root by a cube root or a fifth root by a seventh root. It has to be a cube root by a cube root or a square root by a square root. They have to have the same index. And if they do, it's actually pretty easy. All you need to do is multiply the number in front, the coefficient. You'll see here it says mn. So you multiply the two coefficients together, and then you multiply the two radicands together and put it underneath a single radicand. And that's all there is to it. Now, I'm going to say that's all there is to it. Of course, things can complicate themselves. These radicals can be numbers that you could simplify. So you might want to simplify them first before you multiply, just to keep numbers a bit smaller. And I'll show you what I mean by that as we go through some of these. So you'll find that sometimes I might do it one way, you might do it another way, but then if as long as we both are following correct mathematical principles, we may eventually end up with the same answer. So just because you didn't do it the same way that I did doesn't necessarily mean you did it incorrect. You might be just doing it in a slightly different manner, following correct mathematical principles, and still arrive at the same answer. So for example, let's look at the two that I've got here. Well, if I look at the first one, they're both square roots, so that's good. That means I can multiply them together. I think you'd agree they are multiplied because of the brackets here. So this one, this is multiplied by this. Well, according to our property up above, we're just going to multiply the coefficients. So 2 multiplied by -3, I'd get -6. And then I'm just going to multiply the two radicands together and put them underneath a single radical. 14 times 2 is 28. Yeah, well, that's easy. And it is. However, with radicals now become like fractions. Back in middle school, when you started doing fractions, if you were doing fraction work and your answer came out to be 6/12, well, I would guess your teacher probably would say, oh, yeah, you have the right answer, but we don't like that answer to be expressed that way. We want you to reduce that to 1/2. Well, radicals now become the same thing. We just expect, it's not going to state it in the question, it's just expected that every time you have a radical, you're always going to express them in simplest form. So 28 is not in simplest form because it's still divisible by the perfect square 4. Well, this is 4 times 7, so the square root of 4 is 2. Multiplied by that coefficient will be -12, and then you'll have the 7 left underneath it. That would be your final answer. Now this is what I was talking about earlier. So these two, they're both square roots, which is good. I can multiply them together. So I could say, well, I'm going to go right away and go 3 times 5, 15, square root. So now 8 times 48. Right away you might say, well, I don't know how to do that. I have to make my calculator out, which I'm going to do right here. I say, well, 48 times 8. And I get 384. Well, the problem with that, and it's perfectly right, nothing wrong with it, is now I have to try and reduce the square root of 384, which is a pretty big number, and I got to try and find the biggest perfect square I can that goes evenly into 384. Versus you saying, well, how would I do this instead? These radicals that were presented, they both reduce. So let's reduce those first before I multiply. So square root of 8 is 4 times 2. The square root of 4 is 2. Multiply that by the 3. So you'll get 6 radical 2. That's the reduced version of this one. 48 is 16 times 3. The square root of 16 is 4. Multiplied by the 5. You're going to get 20 radical 3. Well, now look how much easier this is, because now it's just 6 times 20. 120. It's never a big deal, the number up front, because I don't have to reduce that. But if you can get this radicand to be as small as possible, that will make your life a whole lot easier. So now the square root of 2 times the square root of 3, square root of 6. I'm done. Versus over here, now I can cheat a little bit because I can see what the answer is. There must have been a perfect square that went into this 6 times. Let's see what it was. 384 divided by 6 was 64. So I would have had to figure out over here, doing it this way, that 384 is 64 times 6. The square root of 64 is 8. 8 times 15 is 120 radical 6. Same answer, but I would argue this one was much easier because the numbers were easier for me to deal with. So that'll be kind of up to you whether you pick. Sometimes students say, oh, I didn't even notice that. I could have reduced those earlier. Would have made my life easier. You don't have to erase it. Just keep going with what you're doing. But I think in multiplication, it'll often be to your advantage to reduce the radicals before you multiply. All right, here's a few more. Well, let's look at what we got going on here. So they're both cube roots, which is good. So that means I can multiply them. Well, let's start with the coefficients. So this one's got 3w in front of it. This one has 5. So I just multiply those together, and I get 15w cube root. Now, I know this, actually, no, it doesn't reduce because there's no perfect cubes that divide into 12. So that doesn't reduce, that doesn't reduce. This variable would have reduced. I'm not too concerned about variables because you're just basically dividing them by 3 or 4 or 2, whatever the exponent, the index is. So they're a little bit easier to deal with. So we'll just leave the exponents and do that at the end rather than doing it multiple times. So I'm just going to multiply these like normal. So 2 times 12, 24. W to the 7th multiplied by W to the 5, W to the exponent 12. Okay, now I got to reduce this. So 15 W. 20, so I'll break this one out. Cube root. So 24 is divisible by 8, which is a perfect cube. 8 times 3. Now W to the 12 is already a perfect cube because I can divide that exponent by 3, so I don't have to do anything to that. Cube root of 8 is 2 multiplied by 15 is 30. The cube root of W to the 12 will be W to, remember, you're going to divide it by the index. So divide that exponent by 3. It's going to be W to the 4 multiplied by W to the 1 that's already out there. That'll become W to the 5. Cube root, the 3 will be left underneath there. And that would be our final answer. This is a monomial out in front of a bracket. So that needs to distribute into here. So I'm going to have to do 2 multiplications. So 5 radical 2 by 5, and then 5 radical 2 by 2 radical 18. Now you may say, well, I can reduce that square root, and you can. But if you kind of look ahead and say, well, wait a second, when I multiply this radical 2 by square root of 18, I'm going to get 36. And 36 is a perfect square. So that's actually going to work out better if I just leave it as it is. Again, it doesn't matter. It'll work out either way. So let's start here. 5 times 5 is 25. And then you got your radical 2. Now you got to take this radical and multiply it by this one. So multiply the numbers in front. Negative 10. The square root of 2 times the square root of 18 is the square root of 36. This doesn't reduce any further, so we're good with that one. However, 36 is a perfect square. So that's going to work out quite nicely. So it's 25 radical 2 minus 10. The square root of 36 is 6. So now I've got 25, square root of 2, take away 60. And that doesn't reduce any further because this is a radical 2 and this term is just a numeric term. All right, we got one more on here to look at. So this is it, as you'll remember, our kind of our introduction to this multiplication. It's important that you realize I've got a binomial multiplied by a binomial. That means this term is going to have to multiply by this one, and then this term is going to have to multiply by this one and this one. This one would reduce. We might want to do that first. Let's do that first. So 3 radical 5 doesn't reduce. 12 is 4 times 3. The square root of 4 is 2 times that 2 is 4 radical 3. 15 doesn't reduce. No perfect squares go into that one. And this one doesn't reduce. So here we go. This one times this one is going to give us 3 radical. So 15 times 5 is going to be 75. Now this one times this one is going to be minus 12 radical 10. This one times this one will be positive 4 radical 45. And finally, this one by this one will be negative 16 square root 6. Now, if you notice, this one and this one are not in simplest form. So we're going to have to reduce those ones. This would be great to get to here, but you would not get full value for a question if you leave radicals that are not in reduced form. Okay, so 75 is 25 times 3. The square root of 25 is 5. Multiplied by the 3 that's already out there, you're going to get 15 radical 5. Radical 10 does not reduce, just stays the way it is. 45 is 9 times 5. The square root of 9 is 3. Multiply that by the 4 that's out there, you're going to get 12 radical 5. So we said it's 9 times 5. Square root of 9 is 3 times the 4 is 12, and that leaves us with a 5 underneath here. Minus 16 radical 6. Well, there's 2 like radicals, these two, so let's group those together. 15 plus 12 is 27 radical 5s. These two are not like radicals, so we just leave those separated. And there you have it. That would be your expanded. So if they say expand or multiply, all means the same thing. Distribute this through the brackets like you would regular binomials from your algebra skills, and then reduce your radicals and collect any like radicals together at the end, and you'd have your final reduced answer. And now we've got a couple more examples, and you'll see on these slides, all of a sudden now we've also got these squares here and another one over here that we're going to make sure we have to learn how to deal with those properly. And the situation here squared is different than the situation here squared. Here, because this is all considered one, you know, sometimes students look at it and say, well, that's not one, it's two different things, but no, it's not. The 5x is the coefficient, radical 2 is out. The other, this would be a single expression squared. But over here, it is a binomial squared. So we're going to have to deal with this one a little bit differently than we do over here. When it's a monomial squared, all we need to do is simply square the coefficient. So when I square 5x, I get 25 x squared. And when you square a square root, so if you had the square root of 2 squared, well, technically what that means is the square root of 2 multiplied by the square root of 2, which would be the square root of 4, and the square root of 4 is 2. Well, we can skip all this stuff. If you square a square root, they're basically inverse processes of each other. The squaring of a square root just wipes out the square root, and you're left with this. So for example, if I had the square root of a happy face in brackets squared, well, that would just wipe that out, and the answer would just simply be a happy face. All right, so if you're squaring a square root, it just gets rid of the square root symbol. All right, so let's go back over here. So I squared this one. Square the square root of 2, we said is going to give us just a 2. And now nothing, I guess I could reduce this if I wanted to. So I'll go minus 2x to the 7th square root. So 12 is 4 times 3. I can't take the square root of x to the fifth, so I'll split it apart into x to the 4 and x. So I've got 50 x squared. Square root of 4 is 2, times that negative 2 will give me negative 4. The square root of x to the 4th is x squared times x to the 7th. Remember, you add exponents when you're multiplying, so that's going to be x to the 9. Square root of 3x. These are going to get multiplied together. They're out front beside each other, so it's negative 200 x to the 11th square root 3x. That would be your simplified version. Now, when we go over to this one, this is a binomial squared. So think back to even quadratics unit in this course. If you have a binomial squared, that we come up with a shortcut, and we just kind of refer to it as the three-step process, where you square the first, you multiply these two together, and then double it. So a times b would be ab, but doubled would be 2ab. And then we square that third term. So notice when you square a binomial, the answer is a trinomial. Of course, the most common mistake that students will make repeatedly is they just square this one and square this one, and they completely ignore this middle term. And you say, well, how come you got to do this? You can try it yourself. Write it out as a plus b multiplied by a plus b, which is what that would mean. And you expand that all out, you're going to get this. So the shortcut is just what we call the three-step rule. And you've all seen that before. I showed it to you earlier in this course. You probably saw it in grade 10 as well. Square the first, multiply these together, and double square the last one. So that's what I have to do here. I have to apply that rule. All right, so it's a binomial squared. Square the first, 25. Now multiply these two together. Now this can cause confusion. It's the number 5 times 4 radical 3. Well, I only multiply the 5 and the 4 together. The radical 3 is not going to change because you can only multiply radicals by other radicals of the same index. So when I multiply these together, it's 5 times 4, which is plus 20. The radical 3 will stay radical 3. Plus, square this one. I'll square the number in front. We will get 16. And we just talked about what happens when you square a square root. It gets rid of the radical. Now we've got 25 plus 20 radical 3 plus 48. Combine those two together. I've got 73 plus 20 radical 3. And that would be it. Final answer. You cannot combine these in any way because this one's a radical 3 term. This is just a regular numeric term of 73. It has no no radical part to it to allow us to combine them together. So you would be finished. Final answer. All right, so if you were able to go through those past slides and kind of get your brain wrapped around everything that just happened, this would be what I would consider to be kind of the grand finale. And if you're able to do this question, I'd be really confident you've got a great handle on multiplying, adding, and subtracting radicals. So again, you might want to pause the video and give this one a try on your own. And then after you come up with an answer, turn on My Solution and see how you made out. Okay, so this one, the first thing I notice is that obviously it's a long, drawn-out process. This one's going to take us a bit of time. I notice that this radical, this one, all of these will simplify. And the fact that I'm going to end up multiplying a bunch of stuff together here, I think the smaller I can get the radicands to be, the easier it'll make my life moving forward. So that's what I'm going to do first. I'm going to reduce all of these radicals. So the first one is just going to stay radical 6 minus, sorry, I want to get rid of that. So I'm going to simplify this first. And it will be 4 times 3, the square root of 4 is 2, so that's going to make this 10 square root 3, so that r squared, minus 32, 16 multiplied by 2, square root of 16 is 4, so that's going to make this 20 radical 2. 2 plus 3. None of those reduce. This does reduce. It is 4 times 2. The square root of 4 is 2 times that 4 is 8 radical 2. 27 is 9 times 3. The square root of 9 is 3 radical 3. So here's the situation we just ran into on the last slide. I have a binomial, 2 terms, squared. So I need to apply this 3-step rule. Square the first, multiply and double. So 1 times negative 10 is negative 10. Radical 6 by radical 3 is radical 18. Oh, I forgot to double the number in front. So the number in front is going to be 20. Now when you square the last one, regardless of whether this is plus or minus, it's always going to be a plus because you're creating it by squaring. So I square negative 10, I get 100. And then when I square the square root of 3, I get 3. So there is the 3 steps. Square the first, I multiplied and doubled the number in front. Now sometimes students say, well, how come you didn't double this number? Doubling means multiply by 2, not radical 2. So if you're multiplying by 2, that's only going to impact the number in front, not the radicand. That's why that one stayed radical 18 and didn't double. All right, over here now I've got 3 things multiplied together. I have this multiplied by this, multiplied by this. The order you multiply those is going to be your choice. I would recommend that you multiply the 2 binomials first. So I'm going to just leave minus 20 radical 2 for now. And I'm going to multiply these 2 binomials. So 2 times this will give me 16 radical 2. 2 times this one will give me negative 6 radical 3. Now, 3 radical 2 by 8 radical 2 is going to be 3 times 8 is 24. Now, here's another little shortcut. If you have the square root of 2 times the square root of 2, square root of 2 times the square root of 2, the answer is the square root of 4. And the square root of 4 just happens to be 2. Well, as a bit of a shortcut, that'll work every time. If I have, let's say, the square root of 7 times the square root of 7, I'm going to get the square root of 49, and the square root of 49 turns out to be 7. So it's kind of a bit of a shortcut. Anytime you multiply a square root by the square root of the exact same thing, the answer is just going to be that value without the radical sign. And kind of a reason. So another way to write 49 is that it's really 7 squared. Well, the square root of anything squared is just that base. That's why it turns out to be just that 7. So here, when I multiply the square root of 2 by the square root of 2, I'm just going to get a 2. And finally, this one times this one, it's going to be a positive times by a negative. So it's negative 9. Square root of 2 times square root of 3. That's square root of 6. I can keep that in brackets because now the 20 radical 2, I have to distribute it into every one of these. So we've got 6 minus, we can reduce this if we want now just to save us from doing it later. So this is 9 times 2. The square root of 9 is 3. So that's 60 radical 2. 100 times 3 is 300. Okay, now this needs to distribute in all of these. So numbers in front, 20 by 16 will be 320. The square root of 2 times the square root of 2, well, we talked about that earlier, it's just 2. Now you got to watch signs here. It's a negative multiplied by a negative, positive. 120, that's 20 times 6. Square root of 2 times square root of 3, that's the square root of, not 3, square root of 6, sorry. That should be a 6. And where am I now? So this one, again, now multiplied by this one. So 24 times 2 is 48 times just the number in front. So it's going to be negative 960. Radical 2, there's no other radical to multiply it by, so it would just stay radical 2. And then finally, a negative multiplied by a negative, so it's positive. 20 times 9, that's 180. Square root of 2 times square root of 6 is the square root of 12. Alrighty, so now I'm going to tidy up a little bit. So I've got some numbers that I can group together here. And I've got one radical here at the end that will reduce. That's not in simplest form. So we'll tidy that one up and see what we've got here. Okay, so here we go. We've got 6 minus 60 radical 2 plus 300. I'm not really doing much here with those at all. So I'm going to multiply these together. That's take away 640 plus 120 square root 6 minus 960 square root 2. Now the square root of 12 we said is 4 times 3. And the square root of 4 is 2 times 180. So that's going to be plus 360 square root 3. All right, here we go. Let's do the radicals first. And I'll just, to kind of give myself some structure, I'm going to go from highest to lowest. So 120 radical 6. Well, there are no other radical 6s. So the answer for those, when I collect the radical 6s, will just stay 120 radical 6. Next, radical 3. It's the only one, so it's plus 360 radical 3. Radical 2, there are 2 of them, so I got a negative 960 and a negative 60. So when I group those together, I got negative 1020 radical 2s. And then finally our numbers. So I've got 6 and 300, so that's 306. And then I've got subtract 640. 306 subtract 640 is negative 334. So that's going to be my final term out here. And that's it. You would be finished. Now, the one thing I find that students will sometimes think that they can do, which is a shame, if someone was to do all of the work and to get to here would be outstanding. They've got a great grasp of what's going on. But I have seen in the past, then they say, oh, wow, look at all these are divisible by, oh, I don't know, let's say 2. And they divide all of these by 2. You cannot do that unless it's an equation and you're going to divide both sides of the equal sign by 2. This is just an expression. So expressions, you can't divide everything through by constants. You're done. That's your final answer. All right, so that's going to be the end of multiplication and addition and subtraction of radicals. So if you were looking for some practice questions in your textbook, here would be a spot to look. Again, if you don't have your textbook at home, that's fine. You can rely on the PDF version of the files that are listed under our files section and in the general part of our teams.